Welcome viewers, this is Mr. Dingo again here, and today we want to move to how covalent bonds form. In our previous lesson we have looked at dot cross diagrams of covalent bonds and also dative covalent bonds. But today we want now to go a little deeper to be able to understand these covalent bonds. Now viewers, before I start, I want to encourage you to subscribe to our channel. Visit our channel and subscribe to us so that you can support us in this program of trying to educate our children. Now, if I come here to covalent bonds, we previously talked about dot cross diagrams to represent these covalent bonds between atoms. Now, we know that these covalent bonds may be single covalent bonds, double covalent bonds, or triple covalent bonds. For example, if I talk about carbon can have a single bond, it can have a double bond, it can have a triple bond. So this is something that we have seen before, that actually we have these three types of bonds. Now today we know that in this case, when you are doing the displayed structural formulas, you are simply showing these dashes or sticks to represent two electrons. But now we want to go deeper. Now earlier in this class of chemistry, we remember the things we talk about, electronic configuration using the SPDF configuration, the SPDF electronic configuration of different atoms of elements. Now you realize that the SPDF, we know what the S is. These are subshells. So we have the S subshell, we have the P subshell, we have the D subshell, we have the F subshell. Now within these subshells, we know they are orbitals. So the orbital, we know there's only one orbital in the S subshell, and that is, we are going to call it the S orbital. S orbital. And those subshells, those orbitals found inside the P subshell, we are going to refer to them as the P orbitals. So the P orbitals, the D orbitals, the F orbitals, and so on. Now, we know that idea of this, what we call the orbitals. We want now to look at these orbitals. How do they overlap when we have covalent bonds coming in? Do we deal with electrons? How do we deal with electrons in the S orbital? How do we deal with the electrons in the P orbitals? How do we deal with the electrons there? So we are going to mainly deal with the SP orbitals. Now, I want us to start with how single bonds form. Now, single bonds, we know single bonds form when each atom donates one electron to be shared. That's what we call single. For example, in hydrogen is number one. So when they overlap on the ends. You can see that the one end of this and one end of that come here, so that they can overlap in this particular region here. So if you have two atoms of hydrogen here, and they are far apart, and that particular point, we know that the one electron this one has, is orbiting around these particular atoms, and the way they orbit is actually a very regular orbiting, because it's moving regularly. Now when these electrons approach each other, what happens is that these electrons move this one, and this one comes here. Why? Because the nucleus of this atom here pulls some influence on this other electron, and the nucleus of this one also has some influence on that electron. So it tries to attract them, and that's why when they come together, this electron come to this particular point. When they reach this particular point, you realize that there's attraction here and there's attraction there. Other than that, there's also repulsion from this particular nuclei. So this nuclei and this nuclei cannot come so close together, and they also have some attraction, because these are negatively charged electrons here. So the nuclear, the positive nuclear here, the proton that is here is attracting these electrons. This one is also attracting this electron. But also, because this is positively charged, this is positively charged, there's some attraction. That's why sometimes you realize we are going to talk about the bond length. That kind of balance between the attraction between the nuclei and the pair of electrons here, and the repulsive forces between the two nuclei cross a length between the distance between this nuclei and that nuclei, and that's what we call a bond length. So we are going to talk about bond lengths later on and how they relate to the strength of bonds, how bond length affects the strength of these bonds. Now, let's come to this particular point. We have said that when these atoms come together, they form what we call a bond. And when they form a bond, you realize that initially the electron densities, before they were together, they were actually evenly distributed because these electrons were orbiting around. But once you bring them together, the electron density then moves between the two nuclei. So you realize that the electron density will be at the center of this nuclei here. That's why you're going to see. So in this other side, we are not going to feel any electron density. The other side will also not have, because now there is something attracting at them at this particular point. So the electron density now there shifts to that particular central position between the two nuclei of these particular atoms. Now, this kind of bond that forms, we know that because hydrogen is only having the s subshell, so we are only going to talk about the s orbitals. Now this is an s orbital linking. When an s orbital links, or two s orbitals come to form one orbital. Now because this now forms one orbital here, after the other part joins with the other one, we form a new orbital at the center which now carries two electrons. That orbital there, we are calling it now, this kind of bond we are calling a sigma bond. A sigma bond here. Sigma, the symbol is very hard to write. Let me say a sigma bond. So this sigma bond is due to single bond only, and in this case we are drawing a sigma bond of the s orbital. The s orbital, you see, it is end to end connecting. But sometimes you realize that you can have a single bond where we have different elements. For example, you can have hydrogen and chlorine. When you have hydrogen and chlorine, you realize that what is happening is that on the chlorine side, we are having the p orbital. On the hydrogen side, we are having the s orbital. Let's look at that. We know that the energy, the electronic configuration is for hydrogen is 1s1. That one of chlorine is 1s2, 2s2, 2p6, 3s2. Then so we have one, this, and then 3p. You know the outer of this one is 7, so p5 here. Now this is the energy shell or electronic configuration of chlorine. We have 2 plus 2, 4, 10 plus 5 plus 7 is 17. This is the electronic configuration, this SPDF electronic configuration of chlorine. So realize that the outer energy shell is in the orbital which of p, not s. So we have now here something that is now forming between an s orbital of hydrogen and a p orbital of chlorine. So we are going to have an end-to-end connection, but now a p orbital is this way. This is an s orbital, simply fairly distributed, but a p orbital of chlorine, we are going to have something like this. So this is how a p orbital looks like. So if I just make them intersect, maybe that one we can see, but let me write chlorine here, assuming we are now, so this one, the one for hydrogen, we're going to see the s orbital, everything is just this one. So this hydrogen, that's chlorine. So we know that the s orbital, the p orbital of this one we know that they are up to how many orbitals here? There are 3 orbitals here. Now the 3 orbitals, we know that these orbitals, if you remember, earlier we talked about electronic configuration using this particular, I'm talking about the 3p. So this one will be this will be this will be this. You realize that only one orbital is not complete. So that orbital here will link with hydrogen. So we are going to have a linkage which occurs like this. This is a linkage that tells us that we are having, let me say that, we are having now, this is the part where the electrons are shared. We are having this a p orbital, this is an s orbital of hydrogen. So you realize that we can have a single covalent bonds between identical elements for s orbital. We are saying something like this. for the p orbitals and an s orbital, we are going to see something like this. What about a single covalent bond between a p orbital and a p orbital? For example, two chlorine atoms. If you have two chlorine atoms, I said this one is still a sigma bond. This is still called a sigma bond. All single bonds are sigma bonds. What about if we talk about now another single bond between linking between two p orbitals? Like in this case, a chlorine atom plus another chlorine atom. We are just going to draw, like I said, let's draw something of this nature, and then another one of that nature, because we have both chlorine atoms have the p linking on the p orbital. We have seen that from the electronic configuration, because in this case these other orbitals are all filled up. So in this case, this is one chlorine atom, this is another chlorine atom. This is where the bond is, or the S, the single bond. This is another sigma bond. So what we are seeing today here is that the sigma bonds can exist in three types. One, when you have the same atoms of the same elements linking, especially on the s orbital, we are going to have a bond like this. When they are linking on two p orbitals, like in chlorine atoms, we are going to have something like this. You realize that both this, and this, the electron density therefore comes between the two atoms. That's what we can see with the sigma bonds. This way electron density will be more. This is another place where electron density will be high. This is another place where electron density will be high. So this is sigma bond between the s orbitals, the sigma bond between two p orbitals, the sigma bond joining atoms with the one s orbital and a p orbital. And in this case, we said we took an example of hydrogen, chlorine, hydrogen, chlorine atom. So we have seen what about the sigma bonds. I want us now to go to double bonds. This was about the single bonds. What about if we have double bonds? We know double bonds can exist, like we have said before. Maybe, for example, ethene molecule has got a double bond. Now let me say ethene. If I draw the displayed formula, this is ethene. This is ethene molecule. I'm so much concerned with here, because I know here, if I have to talk about this particular point here, we know these are the bonds between this and this. We can simply see them, because hydrogen is an S as s orbital, and carbon here probably will be a p, because carbon is 2, 4. So we are going to talk about 2, 1, S2, then for the first one, then 2p, 2s2 again, then 2p2. But to realize that this orbital here, it is not, it's supposed to, if we have we know the p, 2p2, let me say that, then let me try to expand this one. We know that the p orbitals must be 3, so if you have the p orbitals here, they are 3, then what do you expect? 2 electrons will fill 1, this one will be empty. So we realize that there's much to do here. It means that the linkage here will be an S and a P, an S and a P, an S and a P, an S and a P. But that's not my problem. My problem should be explaining what happens in this particular bond here. Now, a double bond, usually we have said that a single bond has purely sigma bonds, and a sigma bond, I said, it only occurs with single bonds. But a double bond now, the linking is between, a sigma bond must be in all bonds. In usually every bond, a sigma bond must be the first to occur. So we are going to have one sigma bond plus another plus one pi bond. So we have a sigma bond and a pi bond forming for a double bond. Now let me invite you to understand something about both pi and sigmas. Pi bonds are much more stronger than sigma bonds, and that's what explains why ethene, if I compare ethane and ethene, whenever there's a single bond, there's a sigma bond. We said that. When there's single bond, sigma bond. So ethane has a sigma bond, which we said is much more stronger than a pi bond. When you come to this particular place, this pi bond here being weaker, we have said there's a sigma bond and a pi bond. The sigma bond being stronger and the pi bond being weaker, that explains that why this ethene can easily react. It can easily undergo addition reactions because we can easily break the pi bond, leaving only one single sigma bond here. So we have to actually understand that pi bonds are much weaker compared to the sigma bonds. Now let me be able to explain here. We have seen that between these atoms, don't look at atoms, we want to look at the orbitals. Between these bonds here, if I draw these two carbons here, first I'm going to have a p orbital forming on each of these bonds here, and another one here, another one here. These are sigma bonds, and we know that these sigma bonds, if I bring these two carbon atoms much more closer, let me do this. Let me do this. So here is where my carbon is, and another carbon is there. You realize that what have you simply, when you see sideway overlapping, what we have been talking about before in single bonds are end-on overlapping, where one end and one end overlaps. But in this case, we have sideway overlapping. You can see that here. So this part here and this part here is where electron density will actually now come to accumulate. So you realize that with the pi bonds, the electron density is not concentrated in one region. It's concentrated in two parts, above and below. Like you can see a sigma, more concentrated electron density here, and another concentration down here. Now this is, both this and this will simply form one pi bond. So don't look at them that this one pi bond, this another pi bond. No, this plus this will form one pi bond. Then between these two here, we are going to have an end-to-end overlapping, which now forms what we call another sigma bond. I don't know whether that is making sense, but let me be able to draw a big particular diagram so that we are able to see how these things form. Because if you understand pi bonds and sigma bonds, then believe me, everything will be okay. Let me be able to draw a much bigger diagram to show how these diagrams overlap. I've said that this region here, this is carbon, this another carbon, and I've said this region here, this where orbitals overlap sideways. So with the pi bonds, we talk about sideway overlapping. Sideway overlapping. With the sigma bond, we talk about side end-on. The end-on overlapping. So that's something you really have to understand. So I've said that if you have this overlapping and this overlapping, it forms one single bond. Don't confuse to say that this is one bond, this another one pi bond. No, this and this is simply one bond. Then we know that for a sigma bond, it must be end-on overlapping. So we must have another bond here coming and another one overlapping this way. So we have bonds overlapping this way. So you realize that here we have a sigma bond. Sigma bond. And here, both this part and this part, we have the pi bond. So realize that, viewers, in ethene we have this kind of particular arrangement here. So here and here, the pi bond, and there's one. Then between these two carbon atoms, we have an end-on overlapping, which now results into a sigma bond. And you remember this will be a sigma bond on the pi, on the what? On the p orbital. Because you said that the s orbital is an end-on, particularly like this. But on a p orbital, we expect this kind of overlapping. That's what we have here. So we have got a sigma bond. Like I said, this bond here is weaker than this one, and that is why alkenes having double bonds are much more easier to go undergo additional reaction. So this is what we get with the double bond, which we normally write as this one. This is what you see. This is what we can see here, where we can say, maybe let's say this one here is this, and this one here is this one here. And I've said that this part here is much stronger than this one because it can be easily broken down. That is about the double bonds. Let me go to the triple covalent bond, which, believe me, viewers, is much more complicated. So we know that we have said that for single bonds we have what? We have the sigma bond. For a double bond we have one sigma bond and a pi bond. So whenever a double bond forms, the sigma has to form first before the pi can form, because sigma is actually the main bond. It up to be everywhere. So the pi bond cannot form before the sigma bond forms. Now let's talk about the triple bond. Now the triple bond is funny because the triple covalent bonds are funny because with the triple covalent bonds, what happens is that we have got one sigma bond plus two pi bonds. That's what we have. So we expect we are going to have two pair of overlapping and then one sigma in between. Let me see, assuming we have, I want to draw something here. Let me say this is the carbon atom. This is another carbon atom. We have them there. So if you have that, we are going to have this thing is kind of very tricky to draw. Let me try to use a different example. Those people who have seen how that bed for kids, like the one we used to put something zigzag here. I want you to imagine that in one particular side we have this kind of overlapping, another one there, one here, one here, one there, one there. Then of course we are going to have one here, and then one there. Now this is going to be hard to see because I'm expecting us to have things that are actually meeting this way, but you know, I cannot create the 3D diagram very easily for us to be able to see. But what I want you to be able to imagine is that if you have the pi bond in ethene, the double bond that we drew before, was this way. If you have this double bond that we had before, and this is one pi bond here, we know that the carbon is here, we know that another carbon is here. Assuming you copy this kind of overlapping, now that this is standing vertical, then you put another one standing this way. I don't know whether that is making sense. One is we have two levels of overlapping here, which is going to be really tricky to see. So if I have a pair of this and this are two. Remember, the carbon atoms are just the way they are, two only. But assuming one is standing this way, then one is moving that way. Those are the orbitals. So we are going to have this one the way it is, vertical, then another one is coming here. Then we know we are going to have the sigma bond, this one here. The ones you see I'm drawing the other direction, which is not really not going to help us, because you expect this one, these two here to link. That is one bond. Then you expect this other one here and the other one, this other one and the other one also to link, forming this one, forming a pi bond with this one. That is a pi bond. Let me say pi 1, that's one pi bond. Then we have another pi 2 here, pi 2 here, that's another bond. Then we have this one, which is the sigma bond. So if you are able to imagine a 3D diagram, that is, it's very easy the way I'm trying to explain here, that you have two planes. one plane is standing straight, another plane is moving horizontally, and so the first plane is linking this way, that's another bond. The horizontal plane is also linking that one bond and one bond the other side. Then at the center here, like we said, we have got the sigma bond. If you try to imagine it the way I'm trying to explain it like that, you are going to be able to understand what I'm trying to talk about. So we have two pi bonds. Like in this case, I said, if I make this, one pi bond is here, another one is here. If you take another plane like this one and put it horizontal like this, another one will be, another one is there, that's another pi bond. Then finally, we have the sigma bond occurring at the center, which is now the main molecular bond. So this is how the bonds in a carbon triple bond occur. So we are going to talk about this one being maybe the vertical plane. This down here will be the another plane like this, but now horizontally to what we have there, that forming this one. Then the center here we have the sigma bond, which is now linking that thing at the central particular point. So we can now understand how this dot cross diagram that we have been drawing actually are now in details, because we have said when you have a single bond, we have only sigma bonds. And sigma bonds can occur between atoms of the same element, especially hydrogen with the s orbital. Then we can also have atoms, for example, chlorine, which are linking on the p orbitals. And then we can have one s orbital and one p orbital in the case of hydrogen and chlorine. Then we have talked about the double covalent bonds. We have talked about having having one sigma bond and one pi bond. And finally, the triple bond in this case, which has been really complicated to explain, because we actually need to see a 3D diagram to be able to visualize what I'm trying to talk about. So that triple bond carries one sigma bond and two pi bonds. Now, like we have said, alkenes are much more reactive, just like alkynes. Like in this case, we have this kind of a functional group of alkynes. It is very much more reactive because it has one pi bond, another pi bond. And we said pi bonds are weaker. They can easily be broken down, but the sigma bond is much more strong. So thank you, viewers. We are going to talk about, next I want to talk about the bond lengths. I want to talk about the bond length before I conclude this area here. And like I said before, when I started, that attraction between covalent bonds occur, and when they do, there is some kind of opposing forces. Some force that want the atoms to come closer, very closer, and some forces that try to make that very impossible. Like I said, if you have two hydrogen atoms coming together, this is hydrogen and another hydrogen here, we said that this is where we have the shared pair of electrons. So this is a positive nuclear, this is another positive nuclear. The attraction has to come here. This is attracted here. But on the same note, there's repulsive force between these two ions here. So we can talk about two different forces. This is repulsion. Repulsion is taking place here. Repulsion. And this one here we can talk about attraction. So you realize that there are two forces. This one tries to avoid or prevent these atoms or nucleus from coming so closer. This one trying to ensure they come closer. So it means that at any one point there will be always a distance between this nucleus and that. They can never be so closely together. Now that distance between one nucleus of an atom and the other nucleus of an atom in a covalent bond is what we call a bond length. Now bond lengths are very important when you are talking about the strength of covalent bonds. You realize that we have what we call bond energies. Bond energy or bond enthalpy is the amount of energy that can be used to break 1 mole of a covalent bond at a particular condition or a standard conditions. Now we realize that bond lengths, what we say that if the bond length is shorter, then that bond is stronger. So when I talk about the bond length and the strength of bonds, it means that a shorter bond has a stronger, is much more stronger than a longer one. I think that is very easy, meaning we can say that the shorter the bond, the shorter the covalent bond, the stronger the bond will be, the stronger the bond is. So that is something that we can easily argue about. Now, for you to compare these bonds, you have to really be also very objective. We have said that we know that if you compare a single bond to a double bond to a triple bond, we know that triple bonds are stronger than double bonds and double bonds are stronger than single bonds. So you cannot tell me that you are going to compare the bond lengths of this triple bond and compare with the bond length of this one and then argue out. No. If you are compare single bonds only, because then you are keeping the number of bonds a constant factor. That is a very objective way of looking at this particular thing. You cannot tell me you are going to compare the bond length of this triple bond and the bond length of this and try to suggest that because this one maybe is shorter, so this one can be shorter than this one because we expect that there's more force of attraction here than we have here. So what we are going to talk about here is that if you are comparing length of single bonds, only compare lengths of single bonds. For example, you can talk about the length of chlorine to chlorine, carbon to carbon, hydrogen to hydrogen. This one, if we compare, we have talked about compare only similar bonds, meaning single bonds on one side, the double bonds on one side. So we are going to talk about if you have single bonds, all of them, then how do we then relate this particular bond? So we say that if I compare these ones here, the lengths, the one that is going to be having a shorter length, bond length, is the one that is going to be stronger among these single bonds. Just like if I compare this carbon with nitrogen here. Between this one and this one here, we can again compare between this one and this one. Which one has a shorter length? The one that has a shorter length, because now they are triple and triple, is going to be the one that is very strong. I want us to give a table here, and the table which carries bond length, so that we can be able to compare this bond length and argue out this some particular points here. Now like I said, we are looking at a diagram, a table that is showing the bond length and the bond strength. The bond strength here actually just indicates the amount of energy we need to break that particular bond. That's what we refer to as the bond strength. And then the bond length is here. We can see the bond length. Like I said before, we can only compare bonds that are similar, meaning if they are single bonds, that's what we compare their bond lengths. We cannot compare single bonds with triple bonds because those are not similar bonds. Now, you see these are single bonds. These are single bonds, like you can see here. We can see the one with the 1.9. So the shortest one is this. But now you realize the shortest one that we are getting here is having 158, and then we have oxygen here having 144. Now this can be now confusing, and I want to explain why that could be a problem. We expect that this one being one of the shortest, the single bond with the shortest bond length should be the one that is having actually that requires the highest amount of energy to break, but that is not the case. Why are the other ones having more energy, require more energy to break, yet this one is the shortest? We expect the value here to be much bigger, probably than even 242. The reason is that if you look at nitrogen single bonds, assuming you look at the nitrogen single bonds here, nitrogen single bond here, I want you to imagine nitrogen. I want you to imagine nitrogen very well. Nitrogen is number 5. So once we have one here, one here, one here, here, let me say dot cross. Then for this one, you realize that in the outer energy shell of nitrogen, we have got 5 electrons. 5 electrons. But if you look at this one very carefully, for this nitrogen, only 3 have been used. For this nitrogen, only 3 have been used, because if I put this one here, this one is for the other one. So only 3 have been used here. So where are the other 2? They are 2 lone pair of electrons. Initially, I talked about them as 2 lone pair of electrons. This lone pair of electrons, they cause some repulsion between them. So while these other ones, we don't expect those lone pair of electrons. For example, if you talk about nitrogen single bond here, we see this is the highest, carbon. It's 347, 347 yes, yet it is 1.154. But this one here is also single bond and has the shortest bond length, but now we have got the energy that it requires is very little. Why? The reason I'm talking about is the existence of 2 lone pair of electrons that is remaining here. And electrons will repel each other. So it means that the lone pair of electrons on this atom of nitrogen and the lone pair of electrons on this atom of oxygen here, what will that cause? Those 2 electrons will try to prevent this the bond of the weaken the force of the nuclear force of attraction to the nucleus and the shared pair of electrons in between here. So that's why we are saying that that's why that particular thing is bringing confusion. That's why you can actually see this one being higher than actually the other one. And that can also happen with this one we see down here. So the existence of lone pair of electrons can affect the bond strength somehow because there's that repulsion case. But when we look at now carbon triple bond and nitrogen triple bond, between carbon and nitrogen, this is 0.11, 0.12. So we know that being nitrogen is the shortest, we expect it to have the highest bond. Let's check the bond strength. This is 945, this 835. That is now adhering to what we are trying to say, that the shorter the bond length, the stronger the covalent bond. You can see the nitrogen here being shorter is having 945 kilojoules, so require that one to overcome the bond, and then this one requires 838 kilojoules per mole to overcome that particular bond. So viewers, these are bond strengths, and you don't need to memorize them, because when examiner wants you to use them, they will be able actually to give you a table or give you this value so that you can be able to compare. So that I've emphasized that please only compare bonds that are similar. And I've said even those similar bonds, discrepancy can arise, for example, with the carbon here and nitrogen, the way we have seen here, that while nitrogen is the shortest, carbon seems to be stronger than nitrogen's single bond. And I've said that is only a reason due to the two lone pair of electrons existing in nitrogen, but we don't have lone pair of electrons existing in carbon. That means that the two lone pair of electrons create some repulsion forces that weakens the covalent bond here that exists between these two nitrogen atoms, making it require very less energy to break. Thank you, viewers. Please, next time we are going to talk about electronegativity. Please subscribe to our channel so that you can support us during this time of Corona.